Hi everyone, so I'm Daniel, and today I'll be presenting the paper Adversarial Sensor Attack on LiDAR-based Perception in Autonomous Driving. And these slides were partially borrowed from the main author, so thank you for him. And this work was done at UCI and University of Michigan. So as everyone knows, there's been emerging technology of autonomous vehicles, and every company is trying to get into the game. So these autonomous vehicles are replacing the human driver by using essentially a litany of sensors, whether that's ultrasound, camera, or LiDAR. And so just a quick refresher. So LiDAR, we essentially have a laser. It's sending out pulses. They're getting reflected by objects and then getting picked up by a photodiode. And because the speed of light is constant, we're able to measure the distance the object away from the laser based on how long it takes from when the pulse is emitted to when the pulse is received. And so for the car, it's able to generate this kind of point cloud around it to perceive its surroundings. Now, these sensors are just one step of the pipeline for how the autonomous vehicle works. So these sensors, the raw sensor data is then piped into a perception module. This perception module then uses pre-processing, machine learning, and post-processing to essentially spit out these obstacles that will have a position in space and a speed. Then it will have a prediction module, which will try and predict where that object is moving relative to the car. And then there'll be a planning module where the car will be like, okay, given that, what's my path that I'm going to take? And it will then translate those into controls, so whether to step on the gas, whether to brake, whether to steer. So when we leave that perception module, essentially we go from that point cloud to now having these bounding boxes and objects in space. So this is kind of the focus of where the research is looking at. So there's been some past work done on camera-based perception and showing that it's vulnerable to adversarial machine learning attacks. So in the picture here, we have this piece of graffiti on the ground, but it's been specially crafted so that the camera on the car thinks it's another car. But clearly any human would have detected this as, oh, it's just a sticker on the ground. And the current approach to solving this kind of adversarial machine learning techniques is that, okay, even if we can fool the camera into thinking there's fake objects, we can use the camera with the LiDAR and use kind of an ensemble approach to fuse these together. And even though maybe the camera picks up some fake obstacles, together we'll get the real set of obstacles around the car. So this paper is exploring, well, what about if we can not trust LiDAR anymore? What if we can also fool LiDAR into producing these fake obstacles? Then this kind of ensemble method isn't going to work if we can fool both of the models in the ensemble. So there is kind of, well, what about if we just do a simple spoofing attack on the system? So we're going to have some kind of photodiode. It's going to pick up those pulses emitted from the car's laser LiDAR system, and then it's going to use some kind of delay component, and then the spoofer will send out its own pulses to the car's detector, and so the car won't be able to tell the difference between the pulses it sent out and the pulses that our spoofer is getting back, or that our spoofer is sending out and it's receiving from that. And using this delay component, we can try and determine, if we increase the amount of delay, the fake obstacle is going to appear farther away. Less delay, it'll appear closer to the system. And so if you can see in the picture there, we have the LiDAR location on the left and the spoofer all the way on the right. And we're in the point cloud the LiDAR builds, we're able to create these fake dots that the LiDAR thinks are there, but really aren't. They're just from our spoofer sending these pulses towards the LiDAR. But those just kind of dots that we can create. So in the paper, they talked about their spoofer setup could produce 60 of these dots. it's not enough to actually make the car think it's a full-on obstacle or object. It just kind of is going to think it's some kind of noise and not actually make any decisions based on it because it doesn't think it's a full object. And the reason for that is one, we're not able to really create enough points, and two, we're not able to craft the points in a delicate enough way to make the LiDAR system and the machine learning model think that's a full-on object.
So one thing do they talk about, or did you like, so the laser is coming out of the LiDAR, right?
Mm-hmm.
So, but that's like a pencil thin beam, right?
Mm-hmm.
So firstly, I guess the photo detector can only pick up when the laser happens to be pointing to the photo detector,
Mm-hmm.
right? Because they don't have photo detectors everywhere. And now they are adding the delay, and now they are generating the return pulse back. But are the detectors at the LiDAR omnidirectional? In the sense, are they able to see the thing coming at from any direction? Because if they're adding the delay, the laser beam has obviously moved somewhere else, right?
Mm.
But the LiDAR detector should still be, does it listen in all the directions, or is the LiDAR detector also directional? Because
It has 16.
huh?
It has 16 channel laser and receiver.
16 channel laser.
Yeah.
So it kind of is sensitive.
Yeah, but I think they did say that there is there is a limit on the amount of degrees you can do,
Okay.
and so I think it was something around 8 degrees or something like that. There is some limitations in terms of that,
Okay.
and also I guess I should mention that the reason why you can do the spoofing is because the pattern and the wavelengths of the car's LiDAR are very predictable. So because they're predictable, then we can time it to be able to pick it up when it's like sync them up because we can predict it. If there was randomness, it would be a lot much probably impossible to mount this attack. So this kind of so if you see in the picture, the left side is like a car that would be the LiDAR system would detect, and then the right is like our kind of spoofed points, but that's not enough for the machine learning model to then think it's an object. So we want to somehow leverage these kind of sparse, kind of crudely manipulable points in a special way to be able to fool the machine learning model into thinking it's an object. So our threat model is that we're going to have a single spoofer, and it's either going to be sitting on the roadside or it's going to be like mounted on some attacker's car in front of the victim vehicle. And we're going to assume that the attacker has full access to, knows everything about the AV system and the machine learning model that the autonomous vehicle is using. And this kind of gets to the point of like Kirchhoff's principle. We don't want to, especially since these sensors are related to safety critical decisions for the car, we don't want to rely on security by obfuscation. We want to assume the attacker knows everything, which is also reasonable since some of these softwares are open source, like Badu's autonomous vehicle software is open source. So we want to assume that they know everything. So just kind of a more kind of background example to help build intuition. So the idea with adversarial machine learning is we want to take some image, like so in this case a panda. If we fed this through our image classifier, it would classify it as panda. But then if we add some kind of specially crafted noise to this panda, and we then feed the union of those together into the classifier, it's going to now detect it as the label that we want it to. So in this case, we change the label just by adding a little noise, even though if a human looked at this panda plus the noise, it would think it's still a panda. And so the idea is that we're going to take some kind of world input or sensor input of X. We're going to perturb it using this perturbation function P, and we're going to get out this output that's basically the panda plus the noise. And then we're trying to craft this objective function J, given some machine learning model and given this perturbed input, so the panda plus the noise, we want to maximize the chance that it's going to be the label of our choice. So in this case, a gibbon, or for us, we want to be a fake object. So this is kind of the pipeline. And what complicates it, the problem, is that unlike with the image classifier, where we're just trying to go from here, the input to the machine learning model, to the output of the machine learning model, with the AV system, we have this pre-processing and post-processing stage. So we have this raw sensor data that gets pre-processed. So the coordinate frame gets transitioned into like the car's coordinate frame. Then we also do some region of interest filtering. So the car is going to get rid of everything outside of the road because we don't care about it. And then it's also going to get mapped to a feature map for input into the machine learning model. And there's going to be a little information loss during that mapping. So we need to account for that when we're doing our perturbation. And then we have a post-processing stage. So the machine learning model basically comes back with this kind of like 2D plane and says, what's the probability that each of the cells in the 2D plane is part of an object? And then we want to, in our post-processing, cluster those together to be like, oh, well, we have all these points that are likely to be objects, so we're going to cluster them. Okay, that's probably an object. Do bounding boxes, and then also classify it as, okay, that's probably a vehicle, that's a pedestrian, and such. So we need to account for both the pre and the post-processing stage. So what we're going to do is we're going to inject some fake data that's going to be from our spoofer into this, and at the end of the day, and so that's going to be modeled as this like P of X function. So X is being whatever's in the surrounding environment already. Then we want to add our spoofing input and get back this X prime, which is the spoofing input, plus whatever is the world around the car. But we can only perturb. Unlike with the image classifier example, we can add whatever noise we want. There's some physical limitations to our attack. So we can only really vary the distance, we can vary the altitude and the rotational element of our spoofed points. And we can only do those by so much, given that we have a spoofer in one location and with so much sensitivity to the equipment. So there's some physical limitations to how we can add this noise. Like, for example, the people were only able to create 60 points. That's a limitation. So once we design our perturbation function, then we now want to try and make it an optimization problem. So we want to find the X prime, so find whatever noise to be able to maximize the likelihood of this post-processing stage spitting out, oh, we have a fake obstacle. And so that's what our objective function we're trying to maximize is. And at the end of the day, what we want is the car to make a wrong decision. So we want the car to do something it shouldn't have because of this fake obstacle we put in its way. So they were able to design those two functions, and then they ran some experiments. So they got some real sensor data traces from the Body Apollo team. So the Body Apollo team, drove around somewhere and have a bunch of data from their LiDAR traces that they have, and so they have access to those. And then they have the open source system. They turned off the camera system, so they're just running the LiDAR system. So in this kind of attack scenario, you'd have to assume you're also, in the real world, you'd have to be assuming you're also fooling the camera system in addition to the LiDAR system. But right now we're just focusing on, can you fool the LiDAR component? And they wanted to model the fact that, okay, in their setup, they could do 60 points, but maybe a less sophisticated attacker could only do 20 or 40. What's the capabilities of that as well? And so their attack basically found that given some like sensor trace, so some location the car was at in the real world, they basically had a 75% chance of finding some kind of perturbation, so some set of spoof points that would then cause the system to think there was a fake obstacle there. So pretty high, and you can see on the graph based on the x-axis, 20, 40, and 60, that if you add more spoof points, you had better chances of it being successful. So potentially, even if you created a better setup for your spoofer and you could maybe do 80 or 100 points, you might even have higher chance of success. And they also, there's like two different bars here. They went into that there's like this optimization technique they did, where they did some kind of like sampling because they had an issue with falling into like local extrema, and to get out of that they had to do some sampling and local optimization, that was able to improve it. But really, maybe there's even a better way of doing the optimization that could lead to even better results. So they then took their attack and they put it into the simulator that Badu uses, and basically were able to prove that the simulation did cause a wrong decision for the car. So in this example, you have the car driving along at 43 kilometers an hour. Then they were able to spoof this fake object here, and the car slammed on the brakes in the simulator. Granted, it's just a simulator, it's not the real world. There are some physical issues with this attack, such as you do have to have some car or something roadside that is able to aim towards the detector in the car's LiDAR. So there are some physical stuff that are still not yet been, like this wouldn't necessarily have as high of a chance in the real world as it did in the simulator. And one other attack they showed is you had a car sitting at a red light. They were able to spoof this object in front of the car. So when the light turned green, the car just didn't move because it's like, oh, well, there's something in front of me and it's too close in front of me for me to go around it. So I'm just sitting at the light, and this could potentially cause like a traffic jam or something. And this is one other of the attacks they were able to show in the simulator. So some of the takeaways is that LiDAR is probably a viable attack vector and something that could be used to attack these autonomous vehicles, but that just spoofing alone isn't going to be enough, that you probably are going to need to use these kind of adversarial machine learning techniques. And also that, like this paper, although it showed that these are these potential attacks, they were only able to prove them in a simulator. There are some kind of real world issues with their attack model that would make it more challenging. So probably more work needs to be done to see if you could actually actualize these attacks on an actual vehicle. And they came up with some potential defenses, but probably the best one is to introduce randomness to the LiDAR. So if the LiDAR is able to send out pulses in a very unpredictable way, or if it's able to maybe change the wavelength in an unpredictable way, something along those lines, then it would be hard for the attacker to spoof it. Or potentially you could have the LiDAR turn off at intervals in an unpredictable way, and then see if there's any input coming in, and if there is, then there's an attacker and such. So probably using some kind of form of randomness would just fool this kind of attack. And any questions?
Okay, thanks so much. Any questions?
What are your thoughts on using something like a camera system for verifying the LiDAR attack? For example, if the LiDAR thinks an obstacle is there, verify in the camera that there is an image that looks like an obstacle that's there. Did they mention that?
So they didn't mention it. They were kind of just saying like, oh, is it even possible to spoof the LiDAR component of it? But as you're saying, it is right that like there is usually an ensemble approach for these systems. So they'll look at both the camera component and the LiDAR component, and then kind of make a decision based on the two together. So they do kind of have this like ensemble approach, but potentially you could think of an attack where you do both at the same time, but that does make it more difficult to mount.
So the simulation they did
Was just LiDAR. They turned off the camera component. Yeah. So they're just trying to see, was this even possible to fool the LiDAR part of it?
Yeah, I think there's some work out there now. So firstly, fusion is what you're talking about, is fusion, and that is in part meant for precisely this issue. There is some work out there actually, the UC-Irvine component of this, where they have shown that the fusion method which is used in Apollo, which is basically the open source software stack from Baidu for motorcycles, can be attacked, but in a slightly different context. So this one is about LiDAR is being used to detect obstacles. But it turns out that in the AV stack, they use the combination of LiDAR, GPS, and inertial sensors, accelerometer and gyro, to figure out where the car is. And kind of the idea is that they have a 3D map of the city. So the LiDAR not only is detecting cars and all, but LiDAR is also serving to localize where the car is. So for example, Westwood, a particular point on Westwood Avenue will look different in terms of the 3D buildings and all that. Right? So GPS gives you location, LiDAR can give you location if you have digital 3D map, and then IMU can do inertial tracking, so it can based upon some known collisions and so they do the combinations of that. And the script has shown that they can, because GPS can be attacked pretty easily, and supposedly normally LiDAR is the most trusted in that scenario because given the 3D map, 3D map, but they showed that they can still attack that algorithm physically. So at least the one in the hole. So it doesn't. So the thing is, yes, you can mount attacks where you exploit weakness of one of the remaining sensors to still mount an attack. So yeah. So I guess short answer yes, we could explore these things, but there is no foolproof method which can say, look, I can. Okay, great. Thanks. Okay, so next one is I'm recording what you're speaking. Hopefully that's okay. By me. By the way, just if any of you don't want to be recorded when you are doing a presentation, just let me know. That's just sound, but
Okay, hi everyone. I'm Zach Harris. I'll be doing my presentation on this paper, Detection of Electromagnetic Interference Attacks on Sensor Systems. So I'll first go into the problem that we're facing here, some background definitions. I will introduce their attack detection method and show how robust it is, and then we will implement it and see it in some experiments and show the results, and I will wrap up with some assessments of the paper. So the problem that we're facing is that we can intentionally induce electromagnetic interference between a sensor and an ADC. So for example, it's in this red area here. At this portion, the analog signal cannot be well authenticated, which means it's an easy opening for an attack to happen. And if the microcontroller uses incorrect measurements in its control decisions, we can have disastrous results. So for example, an attacker signal inserts an EMI here before the ADC. Say we are able to flip the sign bit on the measurement. The microcontroller thinks it's really cold in the room and turns on the heating unit indeterminately. And you either have started a fire or raised your electric bill. So very disastrous results. Now a few background definitions. We're dealing with low power intentional EMI. There's unintentional EMI and also high power EMI that can destroy logic chips and such. We're not dealing with that. So we have two prerequisites for this low power EMI. The first is there has to be a wire that's exposed that connects the sensor to the ADC and that can act like an unintentional antenna. And the second is we rely on the undersampling of an analog to digital converter. What I mean by that is when an analog to digital converter undersamples a signal, you see we have an amplitude modulated waveform on the right. We're able to insert whatever information we want in the lower frequencies of that waveform. So in this way we can exploit and insert malicious information into the system. We can also do this with frequency and phase modulated signals. However, we rely on nonlinear components in the sensors themselves, so that's outside of the scope of this paper. Finally, I'm defining three different types of sensors that we're looking at here. The first is an active sensor. These are ultrasonic and infrared. These emit something and receive it back. We also have powered passive sensors such as mics and thermistors. These require power but only receive signals. And finally, the third is non-powered passive sensors like piezoelectrics. They don't require power and they receive signals. We will mainly be focusing our experiments on the second category. However, the paper makes arguments that all three can be satisfied by their detection method. onto the attack detection. So the premise of an attacker wishes to insert electromagnetic interference into our system. The premise is that we can distinguish when an attack is present in our system by observing the signal output when the sensor is turned off. So essentially what we're going to be doing is we're going to be turning on and off the sensor at random periods of time. So we first pick an n-bit number representing our on and off sequence. So in this case we have a 0101 sequence that we've chosen randomly. So that's our 4-bit number. Next we encode it using Manchester encoding, so we have an on and an off portion for each bit. So you can see the waveform is on at some portion and off at some portion per the secret sequence in each bit. We will take sub-measurements for each bit, and in this case we're taking 2 readings, one when the sensor is turned on and one when it's turned off. And finally, after every n sub-measurements, we'll take an official sensor reading measurement, and that will be our sensor reading. So the premise of this is the attacker has to pass all sub-measurements in order for the measurement to be valid. And finally, I'll define the 2 terms here. A non-zero sample is a measurement from the sensor when it's turned on, and a zero sample is a measurement from the sensor when it's turned off. And you can see the 2 levels there are distinguished in the digitized signal. So we can actually leverage the type of sensor data used in the system. First, if we have a constant physical quantity, essentially we have a sensor that remains constant between measurements. This could be like a thermistor in a room where the temperature is just changing very slightly. We can use that to detect attacks when the sensor is on. In the second case, we have non-constant physical quantities such as microphones that vary quite a bit between measurements. The measurements are no longer flat, so we can't use them when the sensor is turned on. So to give you an example of this detection method, we're going to go through 2 quick cases. The first is for a constant physical quantity, like a thermistor, so our measurements will be flat. The first constraint we will have to tell whether or not the signal is valid is that all non-zero samples must be equal. Essentially, we confirm that all the samples are flat. And secondly, all zero samples must be 0 volts or some zero biased voltage. Essentially, when the sensor is off, we get no signal output from the sensor. So now we're going to assume that the attacker not only knows that we're using this detection method, but he can align himself with the secret sequence. And I'll show even in that case, this method is very robust. So let's say the attacker guesses that the first bit in the secret sequence is a 0. That means we insert electromagnetic interference on the first part of the waveform, and that goes through. So currently the attacker is undetected in the system. Now, since this is the beginning of the measurement, we have a non-zero sample level that we mark and a 0 sample level. Now let's say that the attacker doesn't insert any electromagnetic interference into our system at all. Now the 0 sample level remains unchanged, but you see the red dot is the new non-zero sample that we just took, and it doesn't match our previous measurement, which means either the attacker attacked our previous sub-measurement or the current sub-measurement. So this implies, and from our first constraint, that the attacker must attack at each sub-measurement, which actually makes this very robust as a detection method. So since the attacker has to attack each time, we guess again. In this case, we guess wrongly and we insert electromagnetic interference when the sensor is turned off. In this case, both measurements don't line up with our original levels, and we know that the attack is going on. And finally, if we do what's called a blind attack or a dumb attack that the paper mentions, we just insert EMI in both parts of the waveform. The 0 sample is off, however the non-zero sample goes through, but we still detect that an attack is being taken place, is happening. So this is a very robust method. We must guess the sequence not only perfectly, but each time. And this is how we get a very robust system if we have a constant physical quantity. Now, it changes if we have a non-constant physical quantity. because we can't leverage the flatness of when the sensor's turned on. So now we have this band where we don't know if an attack is going on in the non-zero samples. So essentially, the attacker doesn't need to insert EMI each time now. You can see that the second submeasurement you see passes because we can't detect that lack of EMI that they didn't put in. So essentially now the attacker can tune how many times they want to try inserting EMI into the system. And if they try k number of times per measurement, they have a 1 out of 2 to the k chance of getting the whole measurement right, because they have a 50-50 per bit of guessing the right time to put the EMI in. So essentially we have two trade-offs. For the defender, we have a security versus performance trade-off, because if we choose a very large N sequence, we're more resilient to attacks. However, it takes a longer time for us to take an actual sensor measurement. So in this case, it all depends on the performance of our system and those requirements. For the attacker's perspective, we have a trade-off between stealth and impact. If the attacker chooses a small k, we can easily achieve an attack because we have more likelihood of getting one through undetected. However, we have a small impact to the system overall because we're not inserting as much electromagnetic interference into the system. So with all this in mind, I'm going to show two experiments which demonstrate this method for both the non-constant and constant physical case. So the first one is dealing with a microphone. We have a non-constant physical system because the microphone is dealing with constantly changing waveforms. So we have an audio signal coming from a speaker 10 centimeters away from the sensor, and we have an attacker who's stationed an omnidirectional vertical antenna also 10 centimeters away from the wire. So just to demonstrate that we can actually attack the system, you'll see that the blue waveform is from a speaker that the microphone is picking up, and the orange waveform is from a 1 kilohertz signal modulated on a 144 megahertz tone that we insert using the antenna. And it has a Pearson's correlation coefficient of 0.93, so it's very similar to the original waveform. So we can get away with inserting some malicious signals into the system this way. So here are the test cases for the system. Case 1 is we just have the speaker, no attack going on whatsoever, but we are using our detection method. Case 2, no speaker is on, except the attacker is trying to insert a signal maliciously, and you can see that the signal is going through. And finally, case 3, we have the attacker and the speaker going at the same time, and you see that the speaker is going at a 1 kilohertz tone, and the attacker is going at a 5 kilohertz, and they're combining in this odd way. For both case 2 and case 3, our detection method is able to detect all points of attack that the attacker tried. These are granted blind attacks where we're simply inserting the whole signal without trying to guess the detection method being used. But for both of these cases, we're able to catch the attacker. And finally, for recovery, the orange line, dashed line here, represents the recovered waveform. And we get a PCC of 0.99 and a very similar signal-to-noise ratio, representing that we're getting a high-quality recovered waveform out. So even with our detection method going, where we're removing samples from our sensor, we're able to recover the original signal with enough granularity. So that's with the non-constant physical case. Now with a constant physical system, we're going to be using a thermistor. The environment is going to be a constant 25 degrees Celsius room temperature, kind of like this room. And the attacker is going to have the same antenna placed 1 centimeter away from between the sensor and the ADC. So this graph is here to show you that as we broadcast an attacking signal, the paper never specifies the type of a signal they're using. As we increase the power of this signal into the system, we're able to change the temperature that's read by the thermistor. So you can see as we increase the power to the right, our temperature goes up to upwards of 38, almost 40 degrees. So we're going to be using this and overlaying it to apply our attack. So our detection results. Again, case 1 is the case when there's no attack going on. You can see that you can easily see our method now of detecting an attack. So these are the time when the sensor is turned off. We have a temperature reference. This is below 0 because we're getting 0 bits from the sensor. The sensor is reading a 25.5 degrees Celsius room temperature reading. Case 2 is when an attacker is blindly inserting information, trying to raise the temperature. As you can see, the peaks are around 40 degrees Celsius now, so we're able to raise the temperature of the sensor. However, the bottom peak raised to around 30 degrees Celsius versus our temperature reference. And this is clear evidence of an attack going on. Finally, we have a smart attack on case 3 to the right, where the attacker is actually trying to guess when what our secret sequence is. You can see that they get the answer right in the first 2 times, and we get a measurement of about 40 degrees Celsius again. We cannot detect those. However, the third sub-measurement that's taken, the sensor's turned off. However, they insert noise there through their system, and we're able to catch the attacker. So with both case 2 and case 3, we're able to detect the attack successfully. So those cases were the ones presented in the paper. They were to demonstrate that we have a system that is very robust to attack now. By turning off the sensor, we're able to detect whether an attack is happening. After reading the paper, these are some notes I have at a second glance. Firstly, the paper mentions that they are arguably remotely interfering. However, in their experiments, the antenna was placed at a maximum of 10 centimeters away from the sensor. So being so close to it, it's arguable whether or not that's remotely interfering. You have to be very, very close. You have to almost take apart whatever appliance you're trying to do this with. Secondly, they don't consider sensor startup or calibration. However, these are analog sensors, so there's not much of that anyway. Thirdly, work can be done to improve the non-constant physical quantities. Those are the ones that are not flat. For example, we can look at a fingerprint or a common pattern that's used in the sensor and base that off of our attack detection as well. So there's some robustness that is missing. Another one is the wire between the sensor and the ADC must act like an unintentional antenna. It must be long enough and it must be exposed in the system, which leads into my final point, which is there are EMI filters that exist that can mitigate this problem before it's even an issue, before an attacker can subject a sensor to this environment. But granted, the system is easily and cheaply deployable, so it's a valid solution to detecting attacks in this way. So that's it for me. That's the end of the paper. If we have any questions.
So, questions, anyone?
So it seems to me that the main method that the victim is able to tell that there's an attack that's going on is by switching on and off the sensor. So when the sensor is off, if there's no signal, it means that there's an attack. But what if the attacker can capture this sensor switching signal and then try to mimic the
But that's where randomness comes in, right? I mean, so you hopefully are using a good random number generator, so the adversary cannot predict it. So there is also one other assumption which I guess you didn't explicitly state, which is that the portion of time where it is 0 or 1 kind of is short enough, and that the adversary can't just look and say, aha, there's a 0 starting, and now I put in a signal, right? Okay.
That's right.
So usually, so adversary in some senses can play the game of detect and then inject. So any detection system would have some delay, and one of the things that works against the adversary is that the shorter the time for detection it has, less reliable its detection would be. So in the sense that it would be, for it to have a reliable detection of whether right now is a 0 or a 1, it has to have a very sensitive detector basically. So that the defender can keep this time small enough relative to the technology that the adversary is likely going to deploy. So I think this strategy is probably not going to work very well for extremely slow. Will not work for some. If there's a relative match between what the current state of detection technologies are that the attacker is able to deploy versus sort of how fast your data is switching. So there's probably some realm of applicability that will work. But having said all of it, I mean, other thing this is saying is shield anything before you digitize, because it's not simply a matter of noise, it's also a matter of attacks in that case. So I think this is a policy sort of issue. Yeah, this work actually builds upon some work in my group where we were attacking not the exposed wire, but we were attacking, remember I had described in one of my lectures the attacking the car braking system with the magnetic field. So there, instead of turning on off the power, we were turning on off the magnetic field that we were injecting. So these guys kind of build upon that. They cite the work in my group, but they apply it kind of in a different setting. But in both cases, we are kind of relying on the fact that the attacker needs some time to detect and mount an attack if it were to do what you are saying. Okay.
Yes, exactly. And something the paper never mentions is the trade-off between applying the system to something or just using a filter, because one could be cheaper than the other, and if you're going to be trying to detect an attack, might as well mitigate it. So they never specify the
there's
trade-off.
another thing though. I mean, I think there are tons of systems out there already, and so the shielding thing, if it didn't happen, it didn't happen. But I think there are two separate messages. Going forward, if you are ever in a position to design a system, don't skimp on pennies because it can be attacked. And the other thing is, as a defense mechanism, I don't know, maybe I'm not making sense, but I was going to say these systems are already out there, but if they're already out there, then the defense cannot be done. So, okay, so they're lost. Yeah, anyway, it's a cute idea, and I guess the bigger message is bringing out is the role randomness plays in defending against attacks. That's a takeaway. Okay, any other questions or comments? Okay, so, thank you.
All right. Hi, everyone. So I'm Hamza, and so the paper I'm going to be reviewing is a view from the cockpit, exploring pilot reactions to attacks on avionics systems. So to give a little bit of background, so of course, airplane flight has become a lot safer than ever in the past few decades, partly due to extensive pilot training. Of course, they have to go through a lot of training in school and all of that, but also due to all the wireless systems that are now being introduced. And basically, with all of these new wireless systems that add some more safety, you also have the availability for like more attacks on these software, using software-defined radios that are a lot more available readily nowadays. And so now it's easier to attack, so you get the safety, but you also have the ability to be attacked. So looking at an actual cockpit for an airplane, you can see how many sensors there are, and so this just gives you an idea of how much can be attacked here. And so to give an example of what might happen when some of these sensors malfunction, just in regular scenarios, in March 2011, in a Delta Airlines flight, there was an inoperative transponder. So basically, other airplanes nearby weren't able to tell that this airplane was here. And so actually, this airplane that was flying through the sky came very close to 3 other aircrafts just within the span of the 10 minutes that this transponder wasn't active. And so nothing happened in this case, but it was quite a dangerous situation. And then actually, in one scenario in 2006, 2 aircrafts in Brazil actually collided. And this was due to a failing transponder as well. And in this case, this was actually, a collision that happened. And so to give an idea of what is the security that currently exists in a lot of airplanes, so actually most of the safety mechanisms that are existing are mainly meant to be withstanding all of the random electronic malfunctions and the mechanical malfunctions. And so this isn't actually taking into account any sort of like any malicious cyber attacks or if someone's trying to actually break your system. So this is more of resilience to any regular failures. And so less emphasis has also, in addition to that, been placed onto the reaction of any of these failures to the flight crew, because you have that human element as well. And so human responses, you can either have something that makes it better, or in some cases worse, if they respond and then they cause even more problems based off of that response. And so this paper, basically, the goal is to examine several wireless attacks that are possible in order to understand first how does the flight crew react to these attacks, and then also look at a few of the systems that need a little bit more security from attacks, and then finally see the effect of training pilots and simulators specifically on the attacks, because that's actually not being done currently. And so to give an idea of like what is the threat model that's being assumed here, so there's lower end threat models that can be used with just even under $3,000 with regular software defined radios and antennas. But in this case, we're going to be assuming around like high-end $15,000 range, and basically using this higher-end threat model, there's a few types of actors we can be looking at. So one of them is just activists, and so these guys are just trying to get some point across and get some attention for their cause, and so they're just trying to cause a little bit of disruption. And then a little more malicious, quite a bit, is like terrorists who are trying to actually create some sort of fear, either just through disruption or actually through destruction. And then finally, the most well-funded of these three types of groups is a state nation, who's in this case trying to destroy some infrastructure, or at least paralyze it. And so in this case, the goals of the attack that this paper looks at is more towards disruption, because of course, if you're trying to do destruction, the first stage is just to disrupt, and then that might cause some actual destruction later. And so what we are looking at is, for example, if a plane is landing and then you have to divert it to a different airplane, that's some type of disruption that might occur. And so the safety systems that we're considering in this paper is there's the ground proximity warning sensor, traffic collision avoidance system, instrument landing system, and these three I'm going to go into a little bit of detail of what they are and how they can be attacked. So first we have the ground proximity warning system. So what this is basically it tells you when you're too close to terrain. So for example, if you're flying over a mountain, for example, you'll know that there's going to be a mountain right below you. And so the way this can be attacked is simply by creating a false alert saying that you're close to the terrain. And then what this can do is this can actually cause your airplane to, when it's landing, for example, do extra go-arounds, wasting fuel, wasting time, and causing some delay. Or sometimes, again, even going to a different airport than you were originally supposed to land at. And so the expected response from a flight crew ideally would be, you ignore the warning in the scenarios where you're landing, because as long as you know basically where you are, you can ignore this altogether. And so there's that human element you need to take into account as well. And then second, we have the traffic collision avoidance system. So what this is this basically is, if you remember, I talked about the Delta Airlines flight where you weren't able to see all the other airplanes that are around you. And so that's actually essentially what you need to know is where are all your other airplanes nearby so you can not have a collision. And so if you actually create false alerts here, then this can actually also make you waste fuel, cause like disruption, and then also sometimes when you see that something like, oh, there's a collision happening, then you may actually go away from traffic control clearances or your regular protocol, and that can also cause more chaos. And so the expected response here is, of course, the first time you see an alert, you should, as a pilot, they should be taking this warning into account. But after a few alarms are triggered, then they should be able to know that something's happening and then maybe turn off the system. And so this is something that, of course, if a pilot doesn't know about this beforehand, then they would never actually know to do that. Third, we have the instrument landing system. So essentially what this does is it allows precise landing in any type of weather scenario or even in poor conditions. And so a way this can be attacked that the paper looks at is actually replicating the signal, but actually saying that you're somewhere else and that you need to land in a place that's further away. And so this can cause you to land, your plane to land in a different location. And so by the time you figure this out, you've wasted fuel and caused a delay and maybe even diverted your aircraft. This could also cause more attacks because it can force the crew to go into a secondary approach, basically, that may also have been compromised. So the expected response here is that the pilot should actually be able to tell from the system itself beforehand that it's been tampered with, and so they should be able to recognize that kind of manually. So the experiment method looking at all three of these attacks is actually to recruit 30 active pilots with varying levels of experience. Of course, they've all had the same training. And basically do 4 runs in a simulator. So essentially, first one is just a regular practice run, and then try each of these 3 attacks and see how they react. And then afterwards, you will basically get some information from their reaction to the attacks, and then also you give them a survey afterwards to say, you know, what is the level of trust, how did this impact you and the safety and basically the workload that you had to do as a pilot. And so the results, this is a little complicated, so I'll explain this on the next slide, but essentially what they did was, you can see the bar is like 30 pilots, the height is 30, and so they're basically giving responses from like a 1 to 5 on a confidence level of how much they were impacted. So I'm not gonna, so this basically explains what were the findings here. So the results for the ground proximity warning system, which basically tells you how close you are to the ground, what they found was that it can actually cause a lot of unnecessary missed approaches on your first landing. But afterwards, then pilots are able to quickly identify that this has been tampered with and then disable or ignore it. Meanwhile, for traffic collision avoidance system, so this one was to tell you if there's other airplanes nearby. This is actually a lot worse because A, it takes a lot longer to detect, and then also B, it's very difficult to deal with for 2 reasons, because you have actually 2 options you can do. First, if there's a lot of alarms that keep going off, you can just ignore it, turn it off altogether. But now you don't know if there's any planes around you, so that's problematic in its own sense. Or you're being distracted as a pilot because you keep getting alarms. So it's kind of a lose-lose scenario in this case, and this is what the results from the pilots basically showed as well. And then finally, we have the instrument landing system. So their experiment basically showed that although this is pretty hard to detect for a pilot, it didn't really cause too much disruption, so it wasn't that bad. And so to give an idea, kind of going back to how easy these are for different groups to do these attacks and how disruptive they are, the traffic collision avoidance system in the middle here is actually the highest cost, but also the highest impact. Meanwhile, the other 2 are not quite as much impact. They're kind of manageable but distracting. And so looking at this from a threat level of who would want to do these attacks, you can see that the TCAS, the traffic collision, is the hardest to do. So that's typically only really feasible for a nation state. Meanwhile, the other 2 are still doable with very low cost, and so that's why they're very feasible for terrorists or activists as well. And so to give a little bit of what the paper said their results were from here is, first, that diagnosis is key. So what this means is that if an attack is happening, sometimes the pilots will know that, yes, there is something going on, but they don't know what. And so they take a lot of time to diagnose what is this issue. And so basically factoring in the attacks into simulators while the pilots are training can actually make their detection and diagnosis time quite a bit faster. And so in that sense, you can see that the simulators, if you train on these attacks, you're actually being very effective at preventing these attacks from being dangerous. And so 93.3% of the pilots from when they were asked said that simulator training on these attacks actually helped them and would be useful. And then second, there's they said that there's a value of the simulation in the sense that if you look at this just theoretically, you can have an idea of what might be some problems you encounter. But until you've actually done a simulation in a real world scenario with your humans, doing all of this scenario, then you can actually see some other factors that you may have missed. And so you have to take into account the human variability. And so the conclusions here, so basically that the traffic collision avoidance system mentioned, it was the most concerning of all of the attacks because it caused inconvenience as well as a potential safety reduction, regardless of whatever course of action that the pilot takes. And then some of the other systems caused some disruption, and they often forced pilots to turn off the systems, but they weren't quite as dangerous. They were more distracting and wasted money, time, but not quite as dangerous. And then finally, basically the main point of this paper was to say that flight simulation for wireless attack awareness, like adding these attacks into your simulation, can help the crew be more prepared and better manage these attacks. And actually one of the things that they said here was that preventative security for these attacks is not really deployable in the near term, so the training is needed in the meantime. And so that was one thing that, looking at it myself, I wasn't sure if that was necessarily how true that was, because, so one of the things, basically, if we go back to the traffic collision avoidance system, for example, the way that they let me actually go back to how this works. what they did here was to create a false alert, and the way that they did this was by creating a false message that was sent to the sensor. And so the reason why this was so easy to do for a third party was actually because through their radio they can just send any message, and the system just takes it for what it is. There's no encryption actually going on, which is actually quite surprising. That's what the paper actually mentioned. So in that sense, let me go back here. And so in that sense, there is something you can do at least in the very short term to at least add some encryption. So that may not prevent these attacks entirely, but you can still kind of make it a little harder to do. But again, in the meantime, before all of these wireless attacks are, you have some sort of way to prevent them. You can at least, basically, the paper is saying, train your pilots to react to them properly through simulation. And so that was the main conclusion of this paper.
But how do they, like during training, what do they propose? Like, how would the pilot decipher it as actually an attack and not malfunction?
Yeah. So essentially,
I guess the question I'm leaning towards is the following: like, it's not that the training is simply inject attack stuff and let the pilot deal with it. I'm assuming that they actually train the pilot how to recognize that this is an attack and how to respond to it. Right?
Yeah.
So what exactly are they proposing doing? Or maybe another way, if they can train to identify an attack, then why can that not be done by a software which basically does the same procedure and then says to the pilot, hey, this looks suspicious?
Yeah, exactly. So that was actually that was basically what I was saying. What they were saying here was that preventative security is going to take a little bit of time to deploy. So essentially what they were mentioning was, in the meantime, it's quite simple to train them in these attacks because you can just add that to the simulator with the attacks that you know of, versus changing your hardware will take a bit of time. So over the, in the next few years, for example, if it may take like 3 to 5 years to actually get this deployed, then yes, you can build a software that will prevent and add encryption, and that should definitely be done. But they were saying in the meantime, since everything is so unencrypted and they never actually had this focus until a few years ago, they're essentially saying that this is the next best course of action in the meantime. That was basically what I got out of this paper.
Questions?
I still have doubt about, there's a reason that there's not enough preventative measures, because all of the attacks that they've shown, these require a very specific SDR setup. For example, in the ILS attack, you'll have to be stationed along the length of the runway.
Yes.
So, what's your opinion on the practicality of these attacks? Do you think that it's
dynamics, right?
Sorry?
Look at our own airport, right? On one side of the runway is a beach, and on the other side are homes. You can certainly be positioned very well to homes.
Yeah, but for example, we'll also have to consider the interference effects in the account. LX is a big airport, and the light slope signals as well as the ILS signals that are present, they are much more powerful than the SDR setups that they're talking about, particularly in this paper. And they also mentioned that they didn't consider the interference effects that might occur here. So
you're saying it's difficult to mount such attacks?
Yeah, I was thinking the practicality of the attacks that they're presenting is quite low.
That's probably true. They actually never specifically tried this out.
Plus, they're stressing a lot on the simulation part, diagnosing between faults as well as attacks. But what we've seen in the paper is that the pilots are able to diagnose the attacks simply using the standard procedures that they have learned in the simulator to diagnose faults. So what do they mean by stressing, trying to train the pilots on simulation? They're already trained to diagnose all of this stuff, malfunctioning TCAS or malfunctioning ILS. We've seen in the simulation results they're using all those standard procedures.
Look, even in a malfunctioning case, so one argument is yes, pilots can rely on other information that they have, right? Not rely purely on the instruments, but that may not be possible under all circumstances and bad weather conditions of this kind of thing, right? So that's one. The other thing is in some of these critical situations, if the pilot is poorly trained, and maybe they'll not react to it in a timely manner. So I can imagine things, but I guess my sort of thought was that if I can train the pilot to identify, then surely I can train an algorithm to do that exactly the same thing, right?
Yeah,
And
that can be.
so it's so to me it seems like if are the attacks so simple that they can easily be detected by a human, or is it that I can mount sophisticated attacks where training will actually not help because they will be hard to detect?
Well, in this case,
but other part you're saying is are they hard to mount? My guess though is that when I look at what goes on in the amateur radio community, the ham community, it's pretty sophisticated stuff out there. So most of the people who are writing these papers, unfortunately, are probably more simple than what's possible. Anyway, that's all.
Question about the methodology. So besides the standard training, could the pilots go into these programs just make an attack, or would they render?
Yeah, that's a good question. So, yeah.
Yeah,
Was
so,
it
so
surprised that
they
were-
weren't told what the attack was. Basically, they knew they were picked, saying that you're going to be getting an attack, but they weren't told in advance what the attack was. And so, of course, that does add an element of bias there as well, that they know that something is going to be happening. And they mentioned that in the paper as well, but they kind of just said, we can't really do anything
There's
about
one
it.
small problem in their setup. Like usually the decisions that are made in commercial jets, the cockpit is usually already. So like one pilot doesn't make any decision. So like, I feel that the stress, the workload, and all the metrics they're showing, I feel that it's like a bit subjective.
Yeah, cool.
So just like every pilot would act differently, and then 2 or 3, it would average down. Someone is having the wrong approach, and the other is having the right approach. So I guess it's sort of similar. So it won't make such a huge difference.
I guess the bigger takeaway for me is the following, that in these critical systems, you can see that how they were designed, assuming that the world was largely non-malicious. So we have everything non-encrypted and all. And given that nowadays everything that can be hacked will get hacked, maybe basically kind of pointing out the obvious that when we train or whatever, learn how to operate anything, be prepared that the causes may not be simply benign ones, and that so from what I read in newspapers and all, right, there are other kind of attacks happening on commercial flights, right? Shining green laser, those are good, right? Powerful, which you can buy off eBay.
I think that's illegal.
It's illegal in this country. It's not illegal in many countries. You can purchase, and I guess probably the act of bringing them in here would be illegal. The other one is the whole stuff around drones. In fact, I was reading this yesterday that in UK now they have passed a law this week, which just basically gives the government the authority to seize any drone. Okay, so because Heathrow had some incidents in the last 6-7 months where people were flying in, I guess even here in California. So I think we have seen people poking these infrastructural systems, and perhaps a combination of training and redoing whatever how we design these systems. I recall you had presented a paper in our group meeting about attack on the localization. Ending. Okay. Yeah. So some of the
The
systems.
wireless attack is actually the same. Like they use it. So like setting SDI parallel to the runway, and that is like a separate attack.
And many airports are in dense urban areas where it's very hard for the authorities to keep track of nothing fishy happening, because it could be leaving Northwest, setting up in LAX, Van Nuys Airport, Burbank Airport. They're all kind of pretty easy to hide, I guess. There was a Bruce Willis movie I recall, which is all about like the terrorists were trying
Die Hard
to
2.
Die Hard 2? Okay, yeah. I mean, it's full of scenarios on how to work with airplanes and airplanes. Yeah. Anyway, good. So, shall we move on to the next one? Thanks.
Okay, the last one for today.
All right. I am presenting my paper on threat to Alexa when commodity Wi-Fi devices turn into adversarial motion sensors. And this is quite an interesting topic because pretty much, as we all know, the homes and office today have tons of these Wi-Fi enabled smart home devices like Amazon Alexa, your PC, your washing machine, your toaster, everything's got Wi-Fi nowadays. And these are all, tossing out all these RF signals into the air, and they penetrate out through the walls of the house, and they're visible to anyone who has the hardware and technical acumen to actually listen in on them. And this opens up potential for attacks on privacy. So someone could come in and snoop on these networks and pretty much turn each of these Wi-Fi enabled devices into motion sensors and figure out where someone could be located in a particular location for the house with a high degree of confidence. And this, of course, could lead to crimes such as burglary, kidnapping, assault, pretty much anything where you need to know the location of a particular target, whether they're home or they're not home, or if they're in a room and you need to get to them, you can get to them using this type of attack. So a little bit of background on device-free human sensing. First off, there's active mode sensing. Most of the existing work in this category pretty much has to do with active mode sensing. This paper in particular does not use it because it has one fatal flaw. Active mode sensing needs to transmit RF signals into the house to create a line of sight. This gives you the advantage that you get like centimeter level precision on where people are located within the house, but it has one major disadvantage in that you can become detected, and then the sensor that you have can be removed by the victim, so your attack is thwarted fairly easily. So passive mode sensing, which this paper does end up using, pretty much only listens in on the RF signals that are being sent outside of the house. They have no control on it. And the time of the paper, the state-of-the-art sensing required a lot of different sniffer devices, as you can see in Figure B down there. You have a bunch of sensors surrounding the house that are listening on these to get good information on where people are located. But the proposed paper method pretty much uses a single sensor and takes advantage of the ubiquity of all the Wi-Fi devices, which are referred to as anchors in the paper, to pretty much obtain this high degree of confidence on which room someone is located based on how they affect the anchors in those rooms. So talking about the attack scenario, we have a ton of Wi-Fi enabled devices, printers, IoT devices, voice assistants, security cameras, smart appliances, lots of things have Wi-Fi. This gives visibility to many, if not every single room within the house or office that you're maybe mounting an attack on. Wi-Fi signal penetration. These signals exit outside of the house, which leaves an attacker the ability to, discreetly store something outside of the location and listen in on these packets without disturbing the network. Wi-Fi protocols don't encrypt source and destination MAC addresses, which leads to an issue where the sniffer can isolate the anchors even under MAC randomization, which there's a separate paper that was linked to showing how to end up doing that. So resource-limited attackers are still able to perform this attack. You can perform this attack with no assumptions made on the number of targets that you have or what their speed throughout the house is. You don't need any physical or remote access to the network. You just need something that can run Wireshark or something that can sniff packets and then store the device outside of the house or office. The attacker only needs to walk by the property once to set the initial bootstrapping for the device that you have that's going to be sniffing these packets. And there's no need for bulky or specialized hardware. You don't need directional antennas, antenna arrays, USRP radios, nothing complicated for this attack. You only need a commodity mobile or IoT device that has an inbuilt antenna, which is pretty common for most of those devices. And the adversary pretty much just partitions the property into a bunch of regions around different anchors. All right, so in terms of how to do this and perform this type of attack, essentially what happens is we'll end up using a new model to capture temporal dynamics of the signal propagation using this particular equation here. Well, what is done is that the amplitude of the channel state information variance, that ACSI, is measured using the received signal strength from each of the frequency subcarriers. And you essentially create the average of the standard deviation of this set of subcarriers at different frequencies, and then denoise the signal to get curves like you see over on the far right there. And this allows for user motion to be pretty distinct. Equipment such as fans and robots, vacuums, they either provide too weak of these sigma values, or they're periodic and can be easily detected and removed from the data. And then dependence on anchor distance. These things work in such a way that, like in figure C down there, if you're closer to the anchor itself, then you'll have a higher spike than if you're further away from it. This gives you some notion on how close you are to a particular anchor in the room, and gives you a higher confidence that someone is in that room. And as you can see on the charts, when there's no one present in the room, it's a very low signal. But when someone's close to the anchor, you have a pretty high sigma value that you obtain. So in terms of sensing ambiguity, there's a couple of things to consider. One, that these sigma values depend on the target anchor distance and the motion pattern or strength, and the attacker has no knowledge of whatever the target behavior is. And two, short physical distance does not always translate to being in the same room as the anchor. Now, there's a bunch of real-world test cases that were performed, and measurements were collected for, like one target staying into a single room. So in the case one here, you'll see that the victim is just walking about the room, and containing anchor A and anchor B. And on the curve, you see that anchor A is definitely being triggered. And in the second case, when they move across into the separate room, there's a period where both A and anchor C are both getting large bumps up because the door was opened. And that leads to a possibility where both rooms may falsely be triggered if smarter considerations aren't taken for analyzing this information. In the third case here, we have the sniffer blocked by an external pedestrian. So having a pedestrian walk near the sniffer device causes a huge spike for all of the individual anchors, which could lead to, again, false positives. So the sniffer needs to be placed in a location that pedestrians can't walk and interfere with. And in terms of external users far away from the sniffer, they have almost no effect on the data. It's pretty much just the ordinary noise that you would get. In another case, multiple users moving around neighboring rooms. Both rooms received spikes for their corresponding anchors, and this scenario ends up being rather successful, as is the users moving in different rooms in the case 6, where you have two non-neighboring rooms with people moving in them, and only A and C are triggered with only just ordinary noise on B. And for case 7, if the anchors are placed too close to a wall and close to other anchors, then you may get false positives in the sense that both A and B are detecting movement, even though there's only someone in room A. So in terms of the attack design, it's going to be broken up into a couple different phases. The first one is bootstrapping. Now in bootstrapping, the adversary is going to be walking around the property, and the sniffer device is going to be measuring the RSS of all the potential anchors and estimating their location within the house. And then you'll move on to phase 2. You plant your sniffer device somewhere, and it's going to run on this rule, where essentially it's going to be looking for some sigma value that's past a certain threshold. And when it passes that threshold for a particular anchor X, then it's going to mark that room as being triggered, and that anchor is being triggered. And some assumptions that get made is that the sniffer will apply a median absolute deviation on all the observed sigma values for each of the anchors. And Gaussian distribution will be assumed when the thing is when each anchor is untriggered. So you just have ordinary Gaussian noise, and that's represented by this equation here, which has this lambda value, which is the essentially the conservativeness factor, and you could set it to different levels. In the paper, it was set to 11, and that gave pretty decent results. For the experiment itself, in terms of there were 11 office buildings that were volunteered for this experiment to be conducted. All the volunteers in the experiment just carried on with their ordinary stuff. They knew that an attack was happening on their privacy and their motion, but they had no idea how exactly it was going to be performed. So in the bootstrapping phase, there were 50 walking measurements of about 25 to 50 meters with over 3,000 RSS measurement traces that were collected. And for the sensing phase, over 41 hours worth of data was collected, and the sniffers were hidden within 2 meters of each of the buildings. And scene 4, scene 6, and scene 8 were just particular floor plans that were publicly available, and then all the anchors and the sniffer locations were then added on to after the fact to see how accurately everything was placed. And in terms of all the different static devices that were located inside of some of the houses, things such as cameras, home voice assistants, smart TVs, smart switches, Wi-Fi routers, surveillance robots, smartphones. All of these were devices that served as anchors in some of these different scenarios. So for the continuous human sensing results, there was 2 different measurements that were used to pretty much quantify how effective this attack was. One was the detection rate, which is essentially just the probability that a room gets marked as occupied by the attack when that room is actually being occupied. And then the false positive rate, which is pretty much the converse, so the probability that room gets marked as occupied by the attack, but that room isn't actually occupied. And in terms of human sensing accuracy, the detection rate scaled with the number of anchors, as well as the false positive rate, as you can see in the table down on the bottom left here. So in this, one reason for this is that the false positives mostly come from impulse noises in the ACSI values that are reported by the firmware, and having more anchors will in turn cause more noise and lead to more false positives. So there is a slight trade-off in terms of that. Well, it's not really a trade-off because the attacker has no control over the number of anchors, but you could potentially, well, I guess you do have some control because you could choose to ignore certain anchors and when you're taking account what you're doing. So you may set a threshold of like maximum of 4 devices per room and then ignore all the other devices. LIFS was pretty much what this was compared against. It's a different sensing type that pretty much relies on the location of each of the anchors. So you'd have to know all the anchor locations ahead of time to use LIFS, so it's kind of an unrealistic example, but even then, this outperformed that other state-of-the-art sensing method. In terms of how accurately the sniffer can adjust to human movement throughout the house. One experiment was done where one person moved between 2 different rooms, and pretty much like on a every 20-second basis, and the sniffer marked the room as being occupied and then switched to not being occupied and then switched back relatively quickly, so it adjusts very quickly to actual human motion. And the error in motion duration estimation is actually quite small. 80% of the cases end up having the error less than 16 seconds, and by the time you get up to 28 seconds, it's pretty much none of the cases have any error past that amount of time. So, in terms of non-human sensing results, it was capable of distinguishing most non-human motion. The only issue that it ran into is that pets are indistinguishable by the system. So large cats and dogs have similar motion patterns to humans when using this. So it is hard to tell whether the movements detections were done by pets or done by actual humans. This could be a potential area for future work to see if it is possible to come up with some sort of way of identifying animals, or maybe even using some sort of defense that relies on large objects that may move around the house to protect against someone trying to do this sort of attack. Moving fans being periodic meant that they were very easy to identify and remove from the data that was received. And Roombas only ever had an effect if the anchor itself was very close to the floor. So otherwise they were never picked up. In terms of defending against this attack, there were a bunch of like naive approaches that you are not necessarily naive, but just approaches that didn't really work too well in general. Like MAC randomization would work really well for bootstrapping and sensing, but the problem is that there's really low adoption for this, less than 3%, and it's not enabled for static devices by default in Android. And this renders it a very poor candidate to defend against this type of attack. Geofencing Wi-Fi signals would really limit the ability to receive these signals, but it comes with an extremely high cost. It's very difficult to deploy and very difficult to configure. And all the methods that involve doing this are either really expensive and undesirable, like painting RF shields around all the walls, or turning down your Wi-Fi or equipping Wi-Fi devices with directional antennas, which is a very expensive thing to end up doing. Wi-Fi rate limiting causes insufficient data points for the sniffer, but limiting the Wi-Fi rate is very undesirable for networks, and it's hard to limit it to a rate where it doesn't exit the house, especially if you have stuff anchors close to the walls. And signal obfuscation makes localization and motion detection quite hard, but again, there's a high energy cost involved and it requires a lot of additional hardware. So what the paper ends up proposing is something using signal obfuscation, but it uses AP-based signal obfuscation. So essentially all the Wi-Fi access points inject customized cover traffic for all the transmitting devices. So you increase your traffic from the router and send out these fake packets that affect the RSS and sigma values for the motion. And in doing so, this has a serious effect on the bootstrapping, because like a 5% increase in the traffic transmission ends up dropping anchor room accuracy all the way down to 35.7% versus the original 92.6%. And there's a serious impact on continuous sensing as well, which cause significant increase in the false positive rate and decrease in the detection rate, making this type of attack pretty much useless when this defense is being employed. So yeah, there's the credits for the figures that I had, and any questions? So.
Any questions?
Yeah.
So for the false positive rates, did they like filter out all of the? You said some false positives can be triggered by spikes in the variance.
Oh, right.
Like, could some of that be filtered out, or did they?
Yeah,
apply all that?
they filtered using the wavelet method on all of the data before they had it. So they tried to filter out all the individual spikes and stuff.
Yeah, so they mentioned that they had problems like identifying separate users when the number of users in the room like increased a certain amount.
Yeah, so like when the more anchors that you have in a particular room, that the noise ends up like adding towards the ACSI noise like adds from each of the firmware devices on there, and that could lead to potential high levels for your sigma values that could then lead to false positives. So an idea could just be capping the number of anchors that you're going to be taking signals from to a certain amount, and then not listening to, like if you have 10 anchors in a room, you only listen to 4 of them instead of all 10, because at 10 you'd get a much higher false positive rate than only listening to 4, and you might end up getting pretty comparable levels of accuracy.
I think they could also use some machine learning or something like that. Like in 2013, I think Professor Dina Katabi, I think she published a paper like see-through walls using Wi-Fi. So there she like showed how you can like identify separate users.
Yeah, but she never scaled it to this extent. In many ways, I mean, this paper is building on that body of work. Okay, they're using kind of similar thing. Actually, last year, I think one of the Wi-Fi access point maker, or Netgear, they announced essentially kind of a subscription service where they basically use the access points at home as a home security system capable of detecting motion. So it's kind of somewhat simplified version of what this paper is talking about. Now, of course, in that case, it's sort of good detecting intruders, whereas this one is more of a privacy invasive perspective. So I think this technology is kind of getting there, and I would probably say given that the access point model has now moved towards companies essentially collecting data, and like the Google Wi-Fi stuff, for example, Google gets all the data and they can play on these games very easily, right? So I think, yeah, these devices are we're letting them image our RF image our homes, basically at this point. Any other comments?
Well, so how easy would it be to make all of these devices implement the mitigation that they used in the paper?
Implementing the mitigation, like for the access points.
For the AP, yeah.
Yeah, I'm not too sure how difficult it would be to actually implement that. I mean, you need to go into each of the access points firmware and have them send out random signals and then have some sort of.
Yeah. I mean, the issue is the incentives are misaligned. Okay, so technically it should be hard, but since these companies have begun to monetize this capability for their own purpose, they will probably not want to do it. That's not good. Hard to say. I think probably, I mean, even like Mac address randomization and all these things are not universally adopted because I suspect in some cases because it's also used for backing for other purposes, like valid and monetizing. So yeah, it's a. So I would say technically yes, but practically. Any other questions? Great. So actually, since our fifth speaker bailed out, so we're going to end early. But I also want to find out. So firstly, sometime tonight or by tomorrow morning for sure, I'll hand out the next Thursday's papers. I think. Okay. One thing. Any comment or feedback on like how I have structured the reviews and the template and the slides? I mean, anything you guys want to change? Not the number of papers you have to review, but anything. No? Okay, great. So I'll see you guys on Tuesday, and I'll send out the next. But tonight sometime. Okay. Yeah, hi. Just give me a second. Let me stop the recording.